In 1999, physicists Lisa Randall and Ramon Sundram calculated the physical distance to a parallel universe. Their math suggested a fully formed reality, complete with its own stars, planets, and laws of physics, could be floating exactly 1 millimeter away from your face. The reason you can't see or touch a universe that close comes down to a strict boundary. Imagine you are a cartoon drawn on a flat sheet of paper. You can move up, down, left, and right, but you can't step off the page. The light we use to see the world is similarly locked on the page, ricocheting inside our reality without ever crossing the 1 millimeter gap to the next. But there is one physical force that ignores these dimensional walls: gravity. If a massive object exists in that neighboring universe, its gravitational pull can cross the void and warp the space we live in. We would feel its weight without ever seeing the source. Because an entire universe carries an almost incalculable amount of mass, its collective gravity acts like an anchor. It reaches across the divide, dragging our galaxies and matter toward the boundary line. Gravity provides the physical bridge that prevents these dimensions from remaining isolated. This loophole allows universes to interact, tugging on each other's structures until they eventually collide. And modern data suggests our universe is feeling the impact of such a collision right now. In 2013, the European Space Agency released data from the Planck Space Telescope. It was built to capture the cosmic microwave background, the fading thermal radiation left over from the Big Bang. The map was supposed to show a relatively even distribution of temperature across the cosmos. Instead, the data revealed a massive temperature drop in the constellation Eridanus. This cold spot was an emptied expanse, stretching 1.8 billion light-years wide. Based on the surrounding density of space, this region should have contained around 10,000 galaxies. Instead, it was completely hollowed out. 7 years before the Planck telescope even mapped this anomaly, physicist Laura Mersini-Houghton had calculated exactly where it would be. Her mathematical models predicted that a collision with a neighboring universe would leave a freezing void in that exact sector of the sky. When this collision occurred, our universe was very young. It hadn't formed solid matter yet. It was a dense, glowing soup of hot plasma. As the parallel universe pressed against ours, its gravity acted like a vacuum cleaner against a piece of fabric. It siphoned out the primordial gas and energy that would have eventually formed those 10,000 galaxies. The Eridanus supervoid provides a physical footprint of this interaction. By mapping where 10,000 galaxies should be, scientists identified a region where matter was violently stripped from our reality during cosmic contact. This contact is an ongoing process. NASA scientist Alexander Kashlinsky tracked the movement of 1,400 massive galaxy clusters spanning billions of light-years. Rather than drifting randomly, these clusters are surging in the exact same direction at roughly 10,000 kilometers per second, moving together like a single river. Moving that much mass at that speed requires a gravitational pull stronger than anything known to exist inside our universe. The anchor dragging them has to be external. Researcher Stephen Feeney scanned the cosmic microwave background for concentric ring patterns, the kind of ripples you see when a stone hits a pond. He found 4 distinct rings in the cosmic radiation, indicating that our universe has been struck repeatedly. Then there is the acoustic data. In 2006, NASA launched the Arcade instrument to listen to the faint radio signals of early stars. When they turned it on, they didn't hear a quiet hum. They recorded a wall of radio frequencies, 6 times louder than the combined noise of every galaxy in the universe. We are looking at a universe being dragged sideways. The flow of those galaxy clusters and the deafening space roar are mechanical symptoms of our dimensional boundary physically grinding against a neighboring universe. The friction between these two universes introduces a severe risk to our physical reality, and the exact scale of that risk was quantified in 2012. That year, the massive particle detectors at the Large Hadron Collider successfully isolated the Higgs boson, the particle responsible for giving all matter its mass. Calculations show that at 125 giga-electron-volts, the Higgs boson sits on a mathematical knife edge. If it were heavier, our universe would be perfectly stable. If it were much lighter, the universe would have collapsed long ago. This specific mass indicates that our universe is in a false vacuum, a state where everything appears calm, but the underlying energy levels have not yet reached their most stable point. To understand a false vacuum, picture a ball resting inside a shallow divot halfway up a steep mountain. As long as the ball stays in that little pocket, everything appears stable. But it isn't at the true bottom of the mountain. A much deeper, true valley lies far below. A universe normally won't leave that shallow divot on its own. It requires a massive burst of energy, a sudden jolt. If the violent friction from a parallel dimension strikes our reality hard enough, it could supply the exact amount of energy needed to push our universe out of the pocket and send it plummeting into the true valley. If we get pushed out of this false vacuum, the underlying rules of physics will break. The forces that bind protons and electrons together will rewrite themselves into something utterly hostile to matter. The moment the universe is knocked from its divot, the impact point will spawn a microscopic bubble of true vacuum. Inside this bubble, gravity, light, and chemistry no longer function the way we know them. The atomic bonds that hold stars, planets, and human biology together simply cease to exist. Once born, this true vacuum bubble will aggressively expand outward in all directions at the exact speed of light, converting everything it touches into this new chaotic state of physics. Because the edge of this bubble travels at the absolute speed limit of the cosmos, you will receive zero warning. There will be no blinding flash in the sky, no distant explosion, and no alarm. The light carrying the visual information of the disaster arrives at the exact same instant as your total disintegration. You are watching this video 1 second, and the next, your atoms are gone. We are sitting on a tiny rock, floating down a cosmic river that is completely out of our control. We cannot steer the galaxies, we cannot stop the friction between dimensions, and we cannot patch a tear in the vacuum. But there is a strange comfort in that lack of control. Despite the invisible threats grinding against the edges of our reality, the conditions for life held together. We survived long enough to wake up, build telescopes, and map the forces outside our own dimension. We exist right now, and that alone is a miracle.